Hello everyone, good day. So today we'll be discussing another method for calculating beam deflections and rotation, and that is virtual work method. So virtual work method is also called a unit load method. So later on we will understand why it is it called unit load method. Now, uh anyway, these are the procedure for that virtual work method. First is we have to establish the moment function of a beam due to the real load. So meaning we are going to apply our knowledge from strength of materials. So in strength of materials, we have a topic of shear and moment diagram. Now, in drawing shear and moment diagram, we have two ways. First is to get to create a moment function, shear and moment function, and the other one is by area method. So dito, we are going to use moment functions. We are going to create an equations that will give us the moment at any point of your beam. That is the first procedure, first step. Next step is to apply a unit load, a point load, unit point load. So that's why this is called unit load method. So we are going to apply a unit load. You have to remove all the real loads, no? And then apply unit load where the slope or deflections will be solved. A unit moment will be applied if the question is the slope. However, if the vertical deviation or sorry, the if the question is the deflection, so you are going to apply a vertical force, 1 unit vertical force to the direction of the unit load, and then its direction will be assumed. Let's say you want downward or upward direction. So also the moment, you can apply clockwise or counterclockwise moment, unit moment. Then later on you will understand kung what's the purpose of the direction of that 1 unit load. Okay, again, first step is to create moment function. Okay, using the real load. Number two is to remove the real load and then apply unit load. Okay, number three is to establish or to create moment functions using that unit load. Is parang uulitin mo yung step number one. But in this case, you're now using unit load. Number four, we are going to prepare a tabular solution. Okay, so which the end column will solve the deflection or rotation of a um certain point of a beam. Okay. So what we're going to do is to take the sum of the last column to determine the slope or the displacement. If the sum is negative, it means that the actual direction of the slope or displacement is opposite to the assumed direction of the unit load. If we are going to recall procedure number two, so we are going to assume a direction. Now that direction, if the answer is negative, meaning your assumed direction is incorrect. Now if the answer is positive, meaning your assumed direction is correct. Okay, now to understand these steps, let's solve this problem. Okay, this is non-prismatic beam. So we have 2EI for beam AB, for segment AB, and for segment CE, we have only I. So for this beam, we are going to determine the slope at B, the deflection at B, slope at C, deflection at C, slope at D, and deflection at D. Again, AC is 2EI and CE is only EI. The meaning AC is stronger than C. Okay, so we're just going to follow the steps provided earlier. So, but before that, of course, you have to solve the reactions to the supports. Okay, that's the first thing to do. Always solve the reactions to the support. So, I I draw here we have here the shear and moment diagram for this beam. Anyway, you don't need to do this. So we'll just recall. the moment functions. As you can see here, this is the moment diagram of this beam. Okay, so you have first degree for A to B, first degree for B to C, second degree curve for C to D, and a third degree curve for D to E. Okay, so this line represented by can be represented by a function or an equation, every line segments or a curve. So meaning if we have here four curves or four lines, so we have four equations that we have to perform. Anyway, you don't have to draw again this moment diagram. Just look on your beam. Okay, depending on the number of non if you have discontinuity of the loadings, for example, biglang nag-change yung load from no load and then you have a concentrated load. Therefore, there's discontinuity of the loading. And there will be one segment, one, one segment, two. There is another discontinuity of the loading. So this is the there's third segment. Okay, so now there's another discontinuity, meaning the loading uh changes. So we have so therefore we have four segment here. Now for this four segment, we are going to create a moment function, individual moment function. So a moment function for the real beam. Okay, so let's start. No. So again, the first thing to do is to establish moment functions of the beam due to the real loads. That is your step number one. So to create a moment function, okay, for segment A to B, which is the cutting section varies, or the distance, this distance x varies from 0 up to 2. So this is your distance x, okay, from the leftmost part of the beam. Okay, again, now your x here is only valid for 0 to 2 meters. Okay. So we are going to create moment functions for each segment. Okay. Now let's take the moment about this cutting section. Again, this cutting section is a known location, which is x from 0 to 2. So all you have to do is to take moment about that point. So considering left, clockwise moment is positive, counter is negative. Okay. So moment about this cutting section. So we have 43.25. That is a positive moment times the distance x. And that's it. Okay, so that's your moment about this cutting section. That is for segment AB. Now let's proceed to segment BC. Okay, for segment BC, so we are now going to extend or to put our cutting section from B to C. And then this cutting section will only move from B to C. Okay, take note that the value of x here is only limited to 2 to 4 meters. Okay, so we are going to sum to cut the section considering left and then moment about that cutting section. Okay, so we have 43.25 times the distance x. Okay, clockwise yan. And then we have counterclockwise 40 about this cutting section. So that is negative 40. And then the distance is, of course, that is x minus 2 meters. Okay. So this is now your moment function for segment BC. We're done with this. Let's move the cutting section to the next segment, which is segment C to D. So in this case, the value of x is only limited for 4. This point is 4 to 7 meters. Okay. So we will just moment all the load to your cutting section. So we have 43.25 times the distance x. Okay, then the 40 counterclockwise is negative times the distance of x minus 2. And then the uniform load, okay, the length of this uniform load is x minus, okay, the length of this uniform load is x minus 4. So the resultant is the counterclockwise negative 5, uh, 5, this is 5 times x minus 4. That is the resultant. And then the distance is x minus 4 over 2. Now you simplify this. This will be 2.5 x minus 4 squared. Okay. Next, we move the cutting sections. Okay. To this point. Take note, class. We are now going to take the moment, okay, of all the loads from the cutting section from left to right, but the value of x will be only limited to your segment DE. Okay, this point and then to this point. Okay, so let's some moment. Or let's take the moment about this cutting section. We have 43.25 clockwise times the distance x, and then 40 counterclockwise negative times x minus 2. And then the uniform load, the length of that uniform load is, so this is your uniform load. We are going to extend it up to here. Okay, so that will be, okay, so that will be 5 times, 5 times the length is x minus 4, x minus 4. That is only the resultant. Then the distance is x minus 4 over 2. Okay, so simplifying, so that will be 2.5 x minus 4 squared. For this triangle, okay, take note that this length is x minus, okay, from the leftmost part, x minus 2 plus 2 plus 3, that is 7. So therefore, the resultant of the triangular load, anyway, we don't have the height yet. Let's calculate this y. Okay, in terms of this y, this is only 15. Okay, so by ratio and proportion, so we have 15 over, okay, the total length is 3, is proportion to y over the length is x minus 7. Therefore, y is equal to, uh, this is 5x minus 7. Now, let's solve the resultant. This resultant is 1 half counterclockwise, so negative 1 half. 1 half of height is 5 times x minus 7, then base is x minus 7. And then the location of the resultant going to the point of the cutting section is 1/3 of x minus 7. So technically simplifying, this will be negative 5 over 6 x minus 7 cubed. Okay, negative. Okay, so that's it. So this is now your moment function from segment AB, BC, CD, and DE. So that is the first thing to do. Moment functions of each segment. Okay. Next step. We are now going to establish moment functions of the beam due to the virtual load. Okay, this is step number 2. So, okay, for this problem, we are going to solve first the slope at B. We are going to solve the slope at. Now we are going to remove the loads because we are now applying 1 unit virtual load. So you have 2 virtual load. Okay. First is concentrated load and the other one is concentrated moment. Okay. 1 unit meaning unitless. Okay. Now, why do we put 1 unit concentrated moment? Because we are going to solve the slope. If we want to solve the deflection, we are going to put 1 unit, okay, 1 unit downward, 1 unit force, okay, 1 unit concentrated. And why is it clockwise, not counterclockwise? Okay, because we are assuming that the slope at this point B is a clockwise. Okay, now, if the value on our final answer is negative, meaning the assumption is not correct, hindi talaga clockwise ang rotation sa point B. Okay, so take note, again, this clockwise moment is just the assumption. Okay, 1 unit. Okay, the clockwise motion is the assumption of the slope at B. Okay, you apply 1 unit moment because we are solving slope. You apply 1 unit concentrated load if you are going to solve deflections. Okay? So now, since you already have here a 1 unit moment, let's calculate the reactions at the supports. So summing moment at E, so we have, let's say, uh, um, okay, so let's sum moment at E to get the reaction at A. So let's assume upward force. Technically, it will be downward na, no? Since this is clockwise about point E, so you should need downward force, downward reaction at A. So negative x times the distance. So this is 10, okay, plus a clockwise moment is equal to 0. These are the only moment about point E. So solving for the reactions, so we have the reaction of point 1 at A, which is downward. Okay, so if this is downward, of course, there are only two forces acting on your beam because we only have a 1 unit load. Okay, again, this is the only load of your beam, the virtual load. Okay, so because you already removed the real load since you're done with the moment functions. These are the reactions of the support. So now we are going to establish moment functions. Okay, due to these virtual loads, including the reactions, no? So we have how many segments? For this case, we only have two segments. Okay, two segments because this is only the discontinuity of the loading. Dito lang nagkaroon ng pagbabago sa loads natin sa point B. So we only have two segments, A, B, and B, E. Okay, so segment AB, let's cut the section here. Okay, segment AB. Again, your X here is only applicable for 0 to 2 meters, from 0 to 2 meters. Okay, so take a moment about that cutting section. So we denote this as small letter M. Here, for real loads, we denote the moment at every cutting section as a large M. Okay, and then we will use later the formula. Okay, so this is your formula for the deflections. And we are just going to put the values here. Okay, we calculated. Okay, so just put here the values. Okay, whatever value we calculated or we solve from step 1 and 2 up to 3. Okay, so now we are going to identify the slope at B. Okay, and then we cut the section, or I mean, cut the section here. We take the moment from segment A to B, for segment A to B. So this is counterclockwise moment, so negative 0.1 times the distance x. And that's it. That is the moment function for virtual load is in solving the slope at B. For segment BE, your value of x here is now limited only to 2 to 10 meters. Okay? Meaning you can only substitute 2 to 2 meters here. So let's take a moment about this cutting section. So we have negative 1 times x and then a clockwise moment. So that is plus 1. So you don't need to put a distance for a moment. Okay. So this is your moment functions for, okay, segment AB and BE, or your whole, okay, beam subjected to 1 unit virtual load. So we're now going to tabulate this. Okay, so this is your, okay, table. So question, how many rows do we need here? So as you can see here, we have 4 rows since we have 4 segments. Okay, 4 rows since we have 4 segments. We just have to copy that here. Okay, then this one, okay, this one, and this one. But on this case, we only have 2 segments, A, B, and BE. So meaning, B to C, C to D, and D to E have the same moment functions for virtual unit. So let's just copy this. This one, you have to copy it to B to C, C to D, and D to E. and they have the same values. Now we are going to integrate this m times m. You're just going to calculate this m times m, this one, okay? So using your calculator, just input, okay, integral of, okay, so 43.25 alpha x. And then you multiply it, okay? You multiply it with this small letter m because that is your formula, mm. Okay, so, or it's just the same. M, larger m times smaller m, or smaller m times larger m. So smaller m is negative 0.1 x. And then take note, the value of x here is only limited from 0 to 2. So you just put 0 to 2 here. And then we can now solve, okay, this integral of dx. Okay, so answer is a negative 11.533333. Yeah. Okay. So next segment, B to C. For B to C, we have 43.25 x minus, okay, minus 40 x minus 2, right? Then for your small letter m, negative 1 x plus 1. And then the limit will be from 2 to 4. Okay, so answer here is positive 125.433. Our next segment, okay, so we have 43.25, 40x minus 2, and then we have another negative 2.5, ay, sorry, 2.5, so negative 2.5, so we're now on third segment, negative 2.5 x minus 4 squared. Okay? And then, same, yung smaller m. Okay, but the limit should be only 4 to 7. Okay, so answer here is 122.9625, 122.963. Okay, so next is the fourth segment. For anyway, if this will not fit on your calculator, you can just simplify this. But if it will be fit on your calcu, so you don't have to simplify. So that it will give you a shorter time of solving this integral. So yan, third segment, and this is cube. Okay, then the limit is 7 to 10. Ay, syntax error. Okay, so 4 is minus 2 minus 2.5 minus 2.5 squared minus 5 over 6 cube. So answer is 28.125. Okay. Now, as you can see here, we have over EI. So since you already have the value of this one, okay, so okay, since you already have the value of this one, which is this one, so all you have to do for the last column, you just have to divide this value by your, okay, EI. Okay, so in our segment, okay, okay, so let's take a look. Segment AB, contains, okay, this is 2EI. Segment BC is 2EI. Segment CD is EI. Segment DE is also EI. Okay, so you just have to divide this value by 2EI. If you have the value of EI, exact value, let's say you have the modulus of elasticity and moment of inertia, divide this by the exact value of EI. However, if you don't have the value of EI, just use this 2, divide this value by 2, and then you have a variable of EI. So divide this value by 2. So since we don't have the exact value of EI, so this will be 5.767, negative 5.767. And then since segment AB is 2 EI, segment BC is also 2 EI. Okay, so we divide this value by 2. Okay. Then since your segment CD is only EI, there will be no changes for this value. Okay, since DE is only EI, okay, the flexural rigidity is only 1 EI, so this value will not change. And then for the answer for the slope at B, so we're solving here the slope at B. Okay, for the slope at B, you just have to sum up, you just have to sum this last column. Okay, so adding this will give you, okay, the slope at B or theta B. So if this is positive, meaning the assumption of a clockwise motion or clockwise rotation, okay, so we assume here that this point B will rotate clockwise as it deflects. Okay, so if this will be positive value, the sum of this will be positive value, meaning your assumption is correct. So let's see if this will yield a positive value, negative 5.767 plus 62.717 plus 122.963 plus 28.125. So answer is 208 positive, 208.038 over EI, which is correct. The assumption for the positive, no, meaning the assumption that B will rotate clockwise is correct. Okay, so this is your answer for the slope at B. Okay, again, the steps are establish moment function for the real load. Next is to remove the load and then apply 1 unit rotation. And we applied here apply 1 unit load to be specific. Now, for slope, you apply 1 unit, okay, moment or 1 unit rotation. For deflection later, we will apply 1 unit downward force. Okay, so that is the slope at B. So next question here is okay, deflection at B. Okay, so for the deflection at B, the first thing to do is to establish the moment functions due to the load. However, this is the best thing here in virtual work method. You don't have to repeat the step 1. If you already have the moment functions of each segment, you don't have to repeat this. Okay, since you can use this on your entire calculations. If it is deflections or slope, you can always use this step number 1. Okay, so the new values here will be the step number 3, which are the moment functions for your virtual work or virtual load. So for the deflection at P, we are now going to apply a 1 unit concentrated load, okay? Because we are solving deflections. Downward downward load means we are expecting that point B will move downward. Okay, point B will move downward. So if the value for the deflections later for the last row or last column is positive, meaning the assumption that point B will move downward is correct. Okay, so now let's establish the moment function. However, we have to solve first the reaction. So the support for this um, virtual load. So the reaction at A, let's assume upward. So x times 10 minus 1. Moment at E, 1 times 8. Okay, so is equal to 0. So answer is 0.8. The reaction at A is 0.8. So therefore, we need 0.2 here so that it will be in equilibrium vertical. So these are the reactions for at the support loaded with virtual unit load at point B, since we are solving the deflection at point. So we only have two segments here. So let's, okay, calculate, or let's form the moment function for segment AB. Let's cut the section at segment AB. Take note that the value of x here is only limited for 0 to 2. Okay, so for moment function for this virtual load, take the moment at about the cutting section. So we have 0.8 times the distance x positive moment. Okay, next, let's move the cutting section to segment B to E, meaning this will be applicable for B to C, C to D, and D to E. Okay. So let's take the moment about the cutting section. So we have 0.8 times the distance x, positive moment. This one, it gives negative moment counterclockwise, times the distance of what? Okay, this distance is x minus 2. So therefore, your moment about the cutting section is this one. This is now the moment functions about the cutting sections of segment B. We will now tabulate the data or using the this table. So again, this value will be fixed on your entire calculations. Whatever slope or deflections you are calculating, whatever point, okay, you are, whatever slope or deflections you are solving, kung nasaan man point siya, you can still use the same moment functions of the real loads. But for the virtual load, small letter m, it will change depending on the point and the locations. Okay, so just put here for segment AB we have 0.8. For segment BC, okay, for segment BE, on the entire segment BC, CD, DE, we have these moment functions. Okay, now we are going to evaluate this integral of small letter m times large M. So we have the integral of, so we have 43.25 x. So we multiply this to 0.8 x. And then the limits will be from 0 to 2. Okay, so answer is 92.267. Next is the second segment, segment BC, 43.25 minus 40 times x minus 2, and then multiply to 0.8x. Okay, this is times minus x minus 2. The limits will be from 2 to 4. Okay, answer is 250.867. Okay, next is the third segment. So we have here 43.25 negative 40x minus 2 minus 2.5, okay, x minus 4 squared. And then we have 6. The limits will be from 4 to 7. So answer is 245.925. And then next is negative fourth segment is for x minus 4 negative. Okay, so we have a fraction here. 5 over 6 of x minus 7. Okay, so cube. And then the limit is, so small letter m, still the same, from 7 to, okay, 10. The answer is 56.25. Okay, so just have, okay, then identify the EI of each segment. Segment AB is 2 EI. You just have to divide this value by 2. So this one, just have to divide. Segment BC is also 2 EI. Divide by 2. Okay, since this segment is only EI, segment CD, the flexural rigidity is only EI. So value will not change. And then sum this value. We just have to add this value. By adding those values, we have 46.134 plus 125.433 plus 245.925 plus 56.25. So answer is 473 positive. Okay, positive 473.742, and that is the deflection at B. Okay, positive, meaning the assumption. Okay, here, that point B will move downward because we apply a downward virtual load. So meaning our assumption is correct. Point B will deflect downward. Okay, so that is the deflection at point B. So next question here is the slope at C. Okay. For this slope, again, we are going to apply a 1 unit virtual concentrated moment or rotation. So at point C. Okay, so if the question is at point B, apply a virtual unit load at that point. If at point C, of course, we will apply a 1 unit unit load, a virtual unit moment. So at point C, so we will assume that the rotation here, the slope here at C is clockwise. Okay? So if the answer later will be a positive value, therefore our assumption is correct. Okay, again, you don't have to repeat this step one, number one, which is establishing the moment functions of due to the real beam. Okay, so having a clockwise moment, solving the reaction at this support. Okay, so let's solve the reaction at the left support. So let's assume, let's say, obviously that is a downward force because summing moment at point A will give you a downward, okay, reaction at the support, left support. So we have x 10 and then plus 1. Okay, for summing moment at point E, 1 times, sorry, that is already a concentrated moment. So that is equal to, so we have negative x times 10 plus 1. So equal to 0. Therefore, the reaction at point A is still a point 1 downward. So therefore, the reaction at E is upward. So having loads, so we have two segments, A to C and C to E. Okay, so let's solve the moment function for segment A to C. By cutting section anywhere between A to C, and that distance from the leftmost part of your beam is distance x. So we have negative zero point 0.1. About this cutting section is counterclockwise. So that is negative zero point 0.1 times distance x. And that's it, no? So yun lang yung moment papunta sa cutting section. Okay, so that is your moment function for segment AC. Then let's move the cutting section to C to E. Okay. So let's take moment about this cutting section. So we have negative zero point 0.1 x plus 1. Okay, so that's it, no? So we have two segments for these loadings. Okay, so let's now tabulate the results. Again, you don't have to repeat this moment function here for the actual or for the real loads. So you just have to copy the moment functions for your virtual loads. So this is for segment A to C. So from A to B, so that is negative 0.1. For B to C is also part of A to C. So we will still use negative 0.1x. For C to E, so this is for two segments already. Negative 0.1x plus 1 and another negative 0.1x plus 1. So we'll just perform this using our calculator. Okay, so we have O integral of 43.25x pinong parenthesis 43.25x for A to B, then multiply to negative 0.1x. The limits is from 0 to 2. His answer is negative 11.535333. Okay, then for segment B to C, so the moment function here will be the large M. So this will be negative 40 times x minus 2. So the limits will be from 2 to 4. So answer is negative 54.067. And then next is we have a negative 40x minus 2 minus negative 2.5 multiply to uh, x minus 4 and then square. Okay, so answer here is negative 52.4. Sorry. Uh, the limits will be 4 to 7. And let's check the small letter m. First, small letter m. Okay, so that should be negative plus 1. And the limits will be 4 to 7. Okay, so we have here 1 to 2 positive. 1 to 2.963. And last one is, so let's change the limits. So we have 7 to 10. Okay, and okay, negative 5 over 6. Then add x minus 7 cube. And this one will not change. The value of m, small letter m, will not change. Okay, so answer here is a positive 28.125. Then, okay, since A to B is 2EI, so just have to divide this by 2. Yan. Then divide this by 2. And nothing change here. And also for this value, same pa rin. So just add these values. Okay, then we'll be having, so that will be, okay, the sum of this value will be the slope at point C. If that is positive, meaning, okay, the clockwise assumption is correct. Again, we assume that the slope here is clockwise because we apply a 1 unit virtual moment clockwise here. So meaning you are expecting a clockwise rotation at point C. So if this is positive, meaning our assumption is correct. Okay, so let's check if this is positive. Obviously, this will be positive. 767 minus 27.034 plus 122.9963 plus 28.125. The answer is 129 positive 118. Negative 5, negative 27, 122. So 118. Okay, 0.287. So that is positive, meaning okay, the slope at C is a clockwise rotation. Okay? And then for the deflection at C, we are going to apply a 1 unit virtual load at point C since we are solving the deflection at C. Okay? So 1 unit virtual load, that 1 unit is a concentrated because we are solving deflection. Okay? For deflection, again, for deflection, a concentrated load. For slope, a concentrated moment. Okay, we also have two segments here. Let's solve first the reactions at the support. Okay, so let's assume upward reaction here. So we have x, okay, times 10 minus 1 times 6. 6, that's equal to 0. Answer is 0.6 upward, so meaning this is 0.4. So we have two segment here, so cut the section at A to B, A to C rather. So take note that the value of x here is limited to 0 to 4 only, meaning A to C is also A to B, then B to C. Okay, later on, if we will try to tabulate this, so for a segment A to B and B to C, katapat niya tong dalawa na to. Okay? Then, let's cut the section at B to C or at A to C, anywhere. So that is a distance x. Let's take moment about dot point. So we have 0.6 times x clockwise moment. Okay, next, let's move the cutting section to C to E. So clockwise is positive. So we have 0.6x minus 1 times the distance. This distance is x minus 4. Okay. So So that's it, no? We just have to tabulate this, okay? And then tabulating, okay? And then just perform this using your calculator. So I hope you can solve this. You try to solve this and check if this is correct. Okay, so the value here is 69.2 for this one, 324, 4.4. Okay, and then 491.85, 112.5. And then divide by 2. Divide by 2, divide by EI, divide by EI. So, we get the sum of this. That is positive, meaning we are correct on assuming that the deflection at point C is downward. Okay? So, that is your answer for the deflection at C. Well, actually, um, same pa rin yan na magiging approach as we try to get the slope and deflection at point D. For slope at point D, we are going to apply a 1 unit rotation at point D. So we will assume that this is clockwise. So assuming this is a clockwise, so the reaction here is downward. The reaction here will be upward. For the slope at D, so we have two segments. Okay, segment A to D. So this X is applicable. The value of X is limited, is bounded to from 0 to 7. Okay, so that cutting section. Okay, now let's take moment about this cutting section. The moment function will be negative 1, 0.1x. And that's it, no? Let's move the cutting section to segment D to E, wherein the value of x is from 7 to 10. Okay, so this is counterclockwise, negative, and this is a clockwise moment, plus 1. That's it, no? Just tabulate for the slope at D. So take note, no? This is for A to D. Meaning, sakop niya na yung hanggang dito sa third row. Okay, A to B, B to C, and C to D. So, let's just input negative 0.1, negative 0.1, and another negative 0.1. And finally, for segment DE, that is negative 0.1. Okay, so negative 0.1 plus 1. And then, perform this, evaluate this. So this value multiplied to this value using your calculator, and the limit is 0 to 2. Answer, and then answer, and okay, then divide by 2, and then divide by 1, divide by 1. Okay, then adding this will give you a negative 152.837. Again, at slope at D, solving slope at D, we apply a concentrated virtual clockwise moment. So meaning we are assuming that the rotation here is clockwise. However, the result gives us a negative value. Therefore, the assumption is incorrect. It should not be a clockwise rotation. It should be a counterclockwise rotation. Okay? That is your answer for the slope at C. For D, okay, for the deflection at D, sorry. This is the sorry that this is the slope at D. We're now solving the slope at D. Slope at D or theta D. Next, let's solve the deflection at D. For the deflection, we are going to apply a 1 unit, the 1 unit concentrated load, because we are expecting that point D will move downward after the deflection. Okay, so let's solve the reactions at the support. So these are the reactions, and then we have two segments because we have this type of loadings. We segment A to D, cut the section anywhere between A to D and that distance x. Take the moment at that point. This is your moment function. Okay? And from D to E, this is your moment function. Okay? Clockwise and counter and negative. Okay? So, and then tabulate. No? Same pa rin yan. Then perform. And anyway, this is for segment A to D. So, for A to D. So, A, B, B, C, C, D. Okay? And then for D to E, then evaluate. Okay? So that is all positive value, meaning divide by 2, a positive, divide by 2, and okay, evaluate this. Okay, the deflection at D. The deflection at D is equal to 739.763 over E. Okay? So it's just a matter of creating moment function. So again, the moment function of your real beam, ah, one time mo lang siyang gagawin. However, for virtual load, ulit-ulit siyang gagawin as long as you solve a slope and deflection at a certain point. Okay? So, anyway, the deflection here is downward because we apply a downward concentrated load. And as we can see, positive ang answer, meaning tama yung assumption. The downward yung deflection. And that's it. So for virtual work method, I hope you understand the concept of using virtual work method and the identifying slope and deflection for a certain beam. Okay? So anyway, for the summary of answers, so these are your answers. Okay, next problem. The non-prismatic compound beam is loaded as shown below. Span ABC has a flexural rigidity equal to AI. This one, the flexural rigidity of this is just EI. However, for C to D, the flexural rigidity is 1.5 EI. So we are going to determine the deflection at C using virtual work. Okay. So let's first is to solve the reactions at the support for this real beam. Because later on we are going to um identify the its moment functions. Okay, so solve the reactions to support. So these are the reactions at the support. So how do we solve that? Of course, you have to isolate first at point C because we have internal hinge. We cannot identify the reactions at the support if we will not cut that point C. Okay, so let's cut at point C. This is 10 kilonewton per meter. Okay, so let's check if these reactions are correct. Those reactions are correct. This is 10 kilonewton per meter. So these are your loads. Okay, so let's assume this is downward, so this is AY, and let's assume this is upward, so BY. The answers are positive, meaning your assumptions are correct. So let's some moment at point C. This is internal hinge. Um, anyway, let's solve first muna yung part na to because we only have one unknown here. I think it would be better to start with this right segment. Cutting section at point C. This is your point C. Okay, this is internal hinge. So we have the reaction dy here. So this is 10 kilonewton per meter. Let's some moment at C so that we can cancel the vertical reactions here. Okay, so we have vertical reaction here. So let's call it Cy. Let's some moment at C clockwise as positive. So negative dy times this is 3 meters times 3. Okay, then negative dy times 3 plus 10 times 3 times 1.5. Okay, so that is equal to 0. Okay, so dy is equal to, so let's solve the value of dy. So it should be 15. So we have transpose 10 times 3 times zero point 0.5 over 3. Answer 15, correct, no? So by summing forces vertical, so if this is 15, so Cy should be, so x plus 15, x plus 15, okay, plus the value of, minus the downward load, 10 times 3, so answer is, oops, so meaning, so that should be equal to 0. Equal to 0, shift to 0. So we assume that the reactions here is upward. So 15 then. So Cy is also 15. So this is 15, this is 15. Both are upward. So meaning if this is upward here, Cy here will be a downward. Okay? Now we can solve the reaction at A. So AY. Okay, let's some moment at point B. Okay, let's some moment at point B. So diretso ko na sa calcu. So AY negative AY. So this is 4 times 4. Okay, times 4. Then the triangular load minus 10.5 times 10 times 4 times 1/3 of 4. 1/3 of 4. Okay, then the uniform load minus 10 times 2 times 1. And then the 15 plus 15 times 2. And that is equal to 0. Shift solve, the value of AY is, oops, that is negative. Now, let me check. Times 4, triangle 10 times 4, 1/3 of 4 minus. Oops, it should be plus. The uniform load should be plus. 10 times 2 times 1. Shift solve. So we have 5.833333 or simply 35 over 6 positive value ang answer, meaning correct ang assumption na downward. This is 35 over 6, correct. By summing forces vertical, this is 35 over 6. Summing forces vertical, we can solve the value of By. So we have negative a 35 over 6 minus 0.5 times. This is triangular load times 4 minus the rectangular load 10 times 2. Then the concentrated downward load 15 and then plus By is equal to 0. So answer is 49. 0.1666 positive, meaning the assumption is correct. Oops, 300. Let me check. Negative 35. Negative 35 over 6 minus triangle point 5 times 10 times 4 minus the uniform load 10 times 2. Okay, minus 15 plus alpha x, okay, is equal to 0. Solve 365 over 6. Okay? So we now solve the reactions of the support. Again, the purpose of this internal hinge is just to solve for the reactions of the support. Okay, this is still determinate beam. If you will try to check the degree of indeterminacy, we're still solving determinate beams. Again, the only purpose of this internal hinge is for you to solve the rotations, or I'm rather the reactions of the supports. Okay, so having the reactions at the support, we can now establish moment functions. Okay, so on this case, we have how many segments for this figure? So for this figure, we have, okay, so the discontinuity of the loading, let's count. We have one, of course, two. So two lang kasi from this point, nag-triangle, then uniformly distributed load. So we have two moment functions that we have to establish. Okay, first this segment A to B. Okay, so let's for A to B, let's introduce a cutting section. So that cutting section is at the distance x from the leftmost part of your beam, and your cutting section will move from 0 to 4. So meaning we don't have specific intensity of that load. So we have to identify the intensity. Let's say this is y. Okay, we solve y in terms of x. So we have y over x is proportion to 10 over 4. Okay, or y is just equal to, so this is 5 over 2 multiply to, or simply 2.5. So let's say 2.5, 2.5x. Okay. Now let's take the moment of this triangular load towards this cutting section. So of course, first is 35 over 6 counterclockwise. So 35 over 6 times x. And this will also gives you a counterclockwise rotation. So which is negative 1/2 of height, 2.5x. I guess we should use fraction form. Okay, 5, it should be 5 over 2x. Okay, so y, 5 over 2x times base, which is x, times the lever arm, 1/3 of x. Now simplifying this will be 5 over 2 times 2, 4 times 3 is 12, negative x cubed. Okay, so that will be the moment of this triangular load towards your cutting section. Okay, so that's it, no? Let's move the cutting section to segment, say C to B to D. So let's take the moment of the loads. Okay. This cutting section is limited only from 4 to, okay, 4 to um, 9, no? 4 to 9 meters. Okay, so let's take the moment about that cutting section. So counterclockwise negative, and the distance x. So we have a triangular load, this triangle. So the resultant is negative counterclockwise about the cutting section, negative 1/2. Height is 10, base is 4, and then the distance is, okay, what will be the distance of the resultant load? Okay, it should be x minus this distance. And what is this distance? That is 2/3 of x. Okay, x minus, sorry, 2/3 of 4. Because this is 4 meters. Okay, 2/3 of 4. 2/3 of 4. So, 2/3 of 4. Now, simplifying this, so we have, okay, so this is 5 times 4, 20. Negative 20 multiply to egg over 3 or negative 2/3 fourths. No, you can just simplify this if you want. Then the uniform load, the uniform load, this is a distance of, sorry, we still have concentrated load. This reaction at B. Likewise, about the cutting section, 3365 over 6. And then a distance of, okay, x minus 4. Okay, this is x minus 4. Then for the uniform load counterclockwise, negative, okay, from negative 10 times x minus 4, the resultant, and then the distance is x minus 4 over 2. So that's why this will be negative 5 x minus 4 squared. And that's it, no? That's your moment function, supposedly. Okay, this is your moment function for B to D. Okay, it should be B to D. Okay, not B to C, no? Okay, B to D. Take note of that. Okay, B to D. So we're done with the moment functions. We only have two segments for this figure. Now we proceed with to stop with the moment functions using virtual load. So for this problem, we are going to get the slope and deflection at point C. Okay, so slope and deflection at point C. So obviously you are going to remove all the loads here. You remove all the loads. So remove this. And then if you want to identify the deflection at point C, apply 1 unit. Okay? 1 unit virtual downward if we are assuming that the deflection here will be downward. Okay, 1 unit virtual load at point C. Okay, so we assume downward deflection at point C. If the answer is positive, meaning the assumption is correct. For this case, we have to solve the reaction at the support. So again, you have to cut the beam at point C and then solve the reactions at the supports. Okay, so yeah, this is your C and this is your 1 kilon, 1 unit load. You also have shear here. And then transposing here, this is shear at C, CY. Okay. Then transposing it here to the other side of your beam. CY will be downward if the assumption here is correct. Then you have your BY. Okay. Let's have moment at point C. Summing moment at point C will give you nothing value here. Will give you reaction here 0. Okay, dy is 0 if you sum moment at point C. So therefore CY is upward 1. Okay, so that is 1. And then downward siya dito 1. And then this is your reaction AY. This is 4, this is 2. This is your CY. Take note. CY to. Okay. Now, summing moment at point A. So we have a summing moment at point A. So BY, what is the value of BY? So negative BY, counterclockwise is negative, times 4 times negative BY times 4 plus CY, which is 1 times 6. So that is equal to 0. Solve. So you have 1.5 by. And then summing forces vertical, this is 1, this 1.5. So this AY should be downward by summing forces vertical. AY should be downward, which is equal to 0.5. Let's check if the answer is correct. Yes, correct. Actually, you have two ways, no, to calculate the reaction to the support. So as you can see here, as we cut the section, okay, as we cut the section earlier, we put the unit, 1 unit load here, okay. You can also put the 1 unit load here, downward, okay, instead of putting it to the right side. Okay, now, solving the reaction here, so we have here Cy. We don't have the summing moment at this point. Of course, this is 0. Summing moment at this point, Cy is 0. Cy is 0. Okay, Cy is 0. Okay, so 1, same pa rin. Okay, if this is 1, 1.5 upward to, this one is downward 0.5. So you can put the 1 unit as if you have a 1 unit on a internal hinge, or if you have a load at internal hinge, you can put it to the left or right side of your cutting section for you to solve the reactions at the support. It will yield the same values of the reactions, no? Kahit saan mo siya ilagay doon sa internal hinge, sa left or right man siya. Okay, so I hope you get that very important concept, no, if you have a concentrated load on the internal hinge. Okay, so we already have the reactions of the support. So from this figure, we have how many segments? Okay, so for this figure, how many segments? So we have from A to B, B to C, and C to D. Okay, so we are now going to establish moment functions for AB first. Let's cut this section. Okay, this is counterclockwise. Okay, so we are solving here the deflection since we apply 1 unit. When you need downward concentrated load at point C. These are virtual. You should be small letter m. Okay, so negative 0.5 counterclockwise times x. Okay, so that's it. No? Next segment, BC. This is for the value of x, which is 4 to 6. Okay, let's move the cutting section. Let's take a moment about that cutting section. Okay, so we have negative 0.5 times x, and then this is clockwise. So plus a plus 1.5 times x minus 4. Let's move the cutting section to the last segment. Then, okay, moment function will be, okay, small letter m. This should be small letter m's. Counterclockwise, negative 0.5 times x. Okay, so negative 0.5 times x, then 1.5 times. This distance is what? X minus 4. And distance, counterclockwise also, this is x minus 6. Okay, so these are your moment functions for the virtual load, and these are your moment function for your real load. All you have to do is to tabulate this. Okay, so we have 3 rows here because kung sino mas marami doon sa real and virtual, it should be the number of rows here. So we have 3 segment here. Okay, so earlier we have 4 segment for the real load. So therefore, we have 4 rows. However, for this one, we have only 2 segment for the real loads. However, for the virtual, three, um, 3 segments. So we need 3 rows here. So we just have to input. Okay, so for segment A to B, it should be, okay, negative 3 over 6x minus 5 over 12. B to C. We don't have B to C here, but B to C is also this one. Okay, because B to C, this is B to C and C to D. And B to D. So meaning we are going to put that here. And then put also here. Then the segment for the small letter m moment functions due to the virtual loads, negative 0.5, negative. And then this one. Okay? And then try to evaluate this using calculator. Okay. So multiply this to this value. The limit should be 46. Okay, just check, no? If these are okay, correct. 104. Please check if these are correct also. Uh, Please check. 60, exactly 60. And this is 0. Okay, this value, so as you try to multiply, will yields to a 0 value. Now, take note, segment AB, if we are going to go back to our figure, segment AB is EI, and segment CD is 1.5 EI. Okay, so therefore, okay, just divide this by EI. We don't have the exact value of EI. Divide this by EI and divide this by 1.5. This is just 0, so will not affect your answer. 0 pa rin yan. Okay? So summing this, so the deflection at C is equal to 164.889. Okay? So that is a downward deflection. Okay, so that's it. I think the only question here is the uh deflection at C using virtual work method. Anyway, we just solved this problem just for you um to identify the if you have a concentrated load, you can put it anywhere, okay? Of your point C or the cutting section, left or right man yan. Okay? So I hope you get the concept of the virtual work method. So thank you guys for listening.